This lesson is on convergency. We shall shortly start to look at maps and charts and try to understand why certain projections are better suited for some applications and other projections are better suited to other applications. We now need to go back to slightly more theoretical studies in order for you to understand some of the concepts we shall need to look at when comparing projections. The topics that we shall study are convergency, conversion angle, departure, scale, and orthomorphism. When we have covered these 5 topics, we shall then be better equipped to compare the Mercator projection, the Lambert's conic conformal, the polar stereographic, and the transverse and oblique Mercator projections. This lesson will describe convergency, which can also be called Earth convergence. Convergency results from the fact that, except at the equator, meridians are not parallel to each other. Meridians originate from a pole, then diverge to reach their maximum distance apart at the equator, then converge back to meet together at the other pole. This means that their angle of inclination to each other is constantly changing. If tangents are drawn to the 2 meridians at the equator, they will be parallel lines in space. At the pole, however, they will converge at an angle equivalent to their difference in longitude. Looking directly down on the pole, there are 360 degrees of angle, and there are 360 degrees of longitude, 180 east and 180 west. Therefore, their angular difference is the same as their change in longitude. At some intermediate latitude, neither polar nor equatorial, the tangents meet in space at some intermediate angle, neither 0 nor the full change of longitude. This angle is known as convergency, or Earth convergence. Convergency is defined as the angle of inclination between 2 selected meridians measured at a given latitude. Both of these elements are necessary to define convergency. For instance, this diagram shows a change of longitude of 60 degrees, and the convergence at the poles is therefore 60 degrees. But if the change of longitude between the 2 meridians had been 40 degrees, the polar convergence would have been 40 degrees. Change of longitude is therefore a necessary part of the definition. However, latitude is as well. For the same change of longitude, the convergency at the equator is 0. At a higher latitude, it becomes an angle of inclination. And at the pole, it has the same value as the change of longitude. Therefore, convergency depends on both latitude and longitude, and both are part of the definition. We can derive a formula to calculate convergency. In order to do this, we will start by comparing convergency at the equator and at a pole. Let's choose 2 meridians 60 degrees apart and draw up a table. The positions we shall choose are the equator and a pole. Latitude at the equator is 0, and latitude at a pole is 90 degrees. The change of longitude in each case is 60 degrees. At the equator, the meridians are parallel. Their inclination to each other, or convergency, is 0. But at the pole, they meet at an angle equivalent to their change of longitude. Divide the convergency by the change of longitude in each case. At the equator, this is 0 degrees of convergency divided by 60. The answer is 0. However, at the pole, we have 60 degrees of convergency divided by 60 degrees of change of longitude. The answer is 1. Look at these angles and these numbers. This is a sine relationship. Here is a sine curve. Let's look at some of the more common values of sines of angles, because these are the ones that frequently come up in questions on general navigation. The sine of 0 degrees is 0. The sine of 15 degrees is about a quarter. The sine of 30 degrees is a half. The sine of 45 degrees is 0.7071. The sine of 60 degrees is 0.866. And the sine of 90 is 1. The relationship between convergency and change of longitude is therefore defined by the sine of the latitude. This gives us the basic convergency formula. Convergency equals change in longitude times the sine of the latitude. Let's now look at what the convergency will be at 30 north, between two meridians 40 degrees of longitude apart. Let's take the tangent at the meridian at 30 north. This is shown by the line x. At y, the tangent looks like this. Let's make a copy of x and move it to y, keeping it parallel. This will make it easier to see the angles. Their inclination at y is the convergency. The formula will tell us what this angle is. The equation is convergency equals change in longitude times the sine of the latitude. Substitute in what you know. The change of longitude is 40 degrees. The latitude is 30 north. And the sine of 30 degrees is 0.5. So the convergency in this example is 20 degrees. We now have a formula for calculating convergency. However, it might not be immediately obvious why a pilot should wish to know what the convergency between two meridians at a particular latitude is. This might be fascinating stuff to a cartographer, but why is it relevant to practical flying? To answer, we need to understand that true north at any point is the direction of the local meridian. For example, if you fly to a different meridian from the point at which you started, your local direction of true north has changed. This is the reason why a run line is a continuously curved line on the Earth's surface. If it did not constantly curve, it could not cut all the meridians, which are at different angles to each other, at the same track angle. However, modern navigation systems such as FMS, INS and GPS use automatic computing to continuously fly the Great Circle track, because in reality it is shorter. Look at the situation on the diagram. An aircraft leaves position X, where the track angle, measured with respect to the local meridian, is as shown in blue. It flies across to position Y, using the great circle track. Its track with respect to space has not changed. A great circle is a straight line in space. However, its track angle with respect to local north has changed, because the two meridians are not parallel to each other. Local true north at position Y is defined by this line. The difference is the convergency between meridians X and Y. This is shown by the yellow shading between the two red lines. Because we are flying from west to east in the northern hemisphere, the direction of true north has moved anti-clockwise with respect to space, from line A to line B. Because we measure clockwise in navigation, the track angle as measured on Earth has increased. That is why great circle track angles change, and it explains the reasons for the rule that you learnt at the start of the course for working out change in direction of a great circle track. If you remember, we drew a circle and divided it into 4 quadrants.